In this segment, we're going to talk about Jovian magnetic field and their associated auroras. Of all the Jovians, Jupiter has the largest magnetic field. It is 100 times larger than the Earth's magnetic field. And therefore, its magnetosphere is 100 times larger than Earth's magnetosphere. So let's go look at Jupiter and Jupiter's magnetic field and Jupiter's magnetosphere. So here we have a cartoon diagram from your textbook showing the planet Jupiter. Jupiter's axis of rotation. So Santa, the North Pole Santa, would be located up there. And it's also showing the magnetic axis, which is slightly off from the rotation axis. So if you had a compass, it would point towards magnetic north as opposed to pointing towards the axis of rotation north, or the north where Santa lives on Jupiter, which I've labeled the axis in green color, as opposed to the magnetic axis, which I've colored a goldish yellow. Now notice we also see this big blue volume area around the planet Jupiter. That blue volume area is called the magnetosphere. The magnetosphere is the volume of space around a planet within which the motion of charged particles is dominated by the planetary magnetic field rather than the solar wind. So what does that mean? To understand what that means, we have to go first look at the solar wind. The solar wind is coming in from the left. So I have drawn, not to scale, the sun is on your left. It is shining, and it is sending out solar wind, which I have drawn as red lines. And that solar wind is charged particles. So think of protons and electrons, charged particles coming out. And that solar wind is coming in towards the Jovian atmosphere. Now the motion of charged particles around magnetic field lines are going to puff up the magnetosphere. So you have lots of charged particles making these motions around the magnetic field lines. The magnetic field lines are drawn as these light blue lines, and the ones on the right are extending out into what's called the magnetotail, and the ones in the front that are shown are making these closed loops. Now the charged particle motions within the magnetosphere are so great that the charged particles coming in from the sun can't push them or squish them down. So the charged particle motions coming in from the sun end up just being deflected around Jupiter, because Jupiter's magnetosphere is so great that the charged particles coming from the sun cannot penetrate. So that's a no, it cannot penetrate. Instead, they get deflected around the magnetic field of Jupiter. So Jupiter's magnetic field protects Jupiter from the solar wind charged particles coming in and hitting the surface of Jupiter. It deflects the solar wind around the planet Jupiter. Now look how large the magnetic field and the magnetosphere of Jupiter is compared to Earth's. So Earth's is drawn in the pink circle down below. You can see that Earth's magnetic field and its magnetosphere is very, very tiny compared to that of Jupiter. Now just like Earth has auroras, so does Jupiter. An aurora is the glowing light display that results when a planet's magnetic field guides charged particles toward the north and south magnetic poles, where they strike the upper atmosphere and excite atoms to emit photons. Now, since Jupiter has the largest magnetic field, you would think that Jupiter would also have the brightest and largest aurora. So let's go look at the Jupiter aurora of all the Jovian aurora. So what we mean by the aurora is this large display of lights at the poles. And here we have enlarged UV images showing you over the planet Jupiter taken in the visual wavelength image from this image from your textbook. So aurora are the glowing light displays that we see at the poles. Now, how do we get these aurora? Let's look at the rest of the definition. So it says, a planet's magnetic field guides charged particles towards the north and south magnetic poles. So what are we talking about here? We're talking about the solar wind particles that are coming in. They're coming in from the sun, and the magnetosphere of the planet deflects the solar charged particles around the planet, but not all of them. Notice that some of them can come into these inner regions where there is no magnetosphere. And so they're coming in. And so the charged particles are being guided into these north and south magnetic poles of the planet. Now let's look at the last part of the definition, where the solar wind particles strike the upper atmosphere and excite the atoms to emit photons. So the solar wind charged particles are coming in towards the poles. And what they're doing is they hit the atmosphere of the planet. And then after they hit the atmosphere of the planet, you start to see these photons, which I'm drawing as blue squiggly lines, and I'll draw them as green squiggly lines. So you have green photons being emitted from the upper atmosphere, and the blue photons being emitted, and that is what you see. You see these colorful displays in the sky of greens and blues. Now you can also see other colors in the aurora, other than greens and blues, but green and blue are the typical colors.